Right, hopefully we are back. Hopefully you can see me. And if I just check, yep, this is the last lesson of the topic. So next lesson we will be just doing like a little bit of a video to revise everything we've done in sound. And maybe some worksheets to help you revise. And then next Wednesday you'll be given the assessment. But for today, let's have a look at what these final learning objectives are. Most of this lesson is going to be spent here comparing longitudinal and transverse waves. Then quite a bit of it is going to be spent here explaining what superposition means, and we're going to spend very little on this bit, recalling that all waves can be reflected. That's very straightforward and simple, and I bet you've had enough of that in the light topic you'll have done, so that'll be a very short bit. So let's start here, comparing longitudinal and transverse waves. Now in lesson 1 we spent a lot of time looking at a diagram that looks a lot like this, and we talked about how sound actually travels. We talked about the speaker pushing forward and pulling back, creating areas of high and low pressure, and we use the term longitudinal wave. Go back and look at that video to really listen to how we talked about the particles moving, etc. I will cover it again in this lesson, but not in as much detail, so do go back to the lesson 1 version. However, when we see a wave that looks like this, with these areas of high pressure, with areas of low pressure in between, or areas of dense particles, if you like, with areas of less dense particles in between, we call that a longitudinal wave. And I said right back in lesson 1 that sound is probably the only one that you will need to know. The only thing that travels by a wave that you need to know is longitudinal will be sound, unless you do triple science, and then they might throw 1 or 2 more in there. So that's a longitudinal wave. Let's just compare that to what a transverse wave looks like to start with. Now, some things, like the water, travel as a wave that looks like this. This is probably like the more familiar shape that comes to your mind. When someone says wave, you think of a water wave, and we have this sort of like up and down movement. So if you're shown a diagram like that, look at the spelling here, transverse. This is a transverse wave. Right? If you see a diagram that looks like this, it could be air particles, it could be a slinky that's compressed. This is a longitudinal wave. But let's really examine the differences between them. And the differences between them is how the particles move. Let's go to the transverse wave for that. This red circle here in the arrows represents a particle of the water, but let's just pretend it's a duck. We've all seen a duck on a pond, and as the waves pass by, the duck just bobs up and down. But what the duck doesn't do, unless it's deliberately swimming, what the duck doesn't do is move along with the wave. The duck seems to stay in position and just bob up and down. And that's because when we have a wave, even though to our eyes it looks like the water is moving to the left or moving to the right, the water's actually just moving up and down. That's all that's happening. So the duck is just pushed up and down. Now this is a characteristic of a transverse wave. So in a transverse wave, the particles will move up and down. Now this green arrow says the direction of travel. Now that's the direction the wave looks to us like it's moving. We could talk about movement of energy, etc. But let's just keep this simple for now. The green arrow, the direction of travel, is just the direction that the wave looks as though it's moving. But we have to bear in mind the water particles themselves are just moving up and down. That's all that's happening. Think of a Mexican wave in a football stadium. When you're watching that on a camera, you can see that the wave looks like it's moving all the way around the ground. But all the people are doing are standing up and sitting down. Okay? So the people are the particles, they're up and they're down, but it appears as though the wave has a direction. And this is, like I said, this is a transverse wave where the particles do just move up and down. And we could go on further. We can say the particles are moving up and down, but the wave is moving to the side. Okay, there's like a 90-degree angle between the way the particles are moving and the way that the wave appears to move. Right, the direction of the wave. They are perpendicular to each other. They're at 90 degrees. Let's have a look at a longitudinal wave. So here's our longitudinal wave. And again, go back to lesson 1 if you've forgotten everything we said about how a longitudinal wave works. It's broken down in detail for you there. But essentially, we said the speaker pushes back and forward. And as a result, if we look at the red dot here, the particles move back and forward. But the sound also travels forward. So this time, they're not at right angles to each other. right? They're kind of parallel, and we can use that word to describe the differences, right? In a longitudinal wave, the movement of the wave and the movement of the particles are parallel to each other, okay? On the same plane, parallel to each other. Whereas in a transverse wave, the movement of the wave and the movement of the particles are at right angles to each other. Now, the thing about sound is, it is a longitudinal wave, but it gets a little bit complicated because we use a piece of equipment when we hold a microphone to something and we look at the sound waves on the screen. When we look at like an oscilloscope on the screen, the sound wave gets turned into a transverse wave. So even though a sound wave looks like this, when we represent it on a screen and we're trying to measure all the wavelengths, etc., trying to calculate the frequency, the screen will turn it into one of these. All right. Now, essentially, the distance between the peaks here is the same as the distance between the compressions, but you don't need to know any of that. Just accept the fact that a sound is a longitudinal wave, but when we see it on a screen, the computer magically turns it into a transverse wave, which is where this third point comes in. Explain what superposition means. It's very difficult to talk about superposition without seeing waves as transverse waves. Now, what do I mean by that? If I have one car here beeping its horn, and I have another car right next to it beeping its horn, what would be louder? Would it be both cars beeping the horn at the same time together, or would it be just one of the cars on its own beeping its horn? Now, your gut feeling will probably be, oh, it's both cars beeping it together, but not always. Okay, and here's why. If we take that sound wave and we reimagine it as a transverse wave, yeah, we know it's longitudinal, but if we draw it on the computer as a transverse wave, just like where I've got my mouse over here, this could be the wave from the first car, the first horn. This could be the wave from the second. And the thing about sound waves is, just like water waves in a pond, they can add together. If I throw a stone in one area of a pond and create a ripple, a wave, I throw a stone in another area and create a ripple or a wave, when they meet in the middle, we can get bigger waves. Now, which would mean a louder sound. Okay, so here, the top one is one of the cars, the bottom one is another one of the cars, and those sound waves, they add together. We call that superposition, right? It's just adding together of waves. And we can see here, right, that they've added together to make a much louder sound. However, that's not always going to happen. They will only add together, and we call that constructive interference. They will only perfectly add together like that if they are kind of lined up. We might use a term in phase, but what I mean by lined up is the top part of this one here is directly underneath the top part of that. The bottom part is directly underneath the bottom part of that, and they've added together to make a bigger wave. But if they're not lined up, right, if they're like meeting each other as a complete opposite, which is what we've got down here, okay, so this could be the first car horn, this could be the second, then they just cancel each other out. We call that destructive interference. And I know how odd that sounds, but in positions where sound waves do that, we can't hear anything. It would be completely silent, okay? And it's a shame I'm not in the lab where I can get a couple of speakers up and have you moving around and you can hear this exact effect. You know, if I've got one speaker on one side of the room, another speaker on the other, as you walk around the room, you'll hear loud sound, you might take a couple of steps, and then you'll hear nothing. And then another couple of steps, you'll hear the loud sound, then you'll hear nothing. Because the sound waves are superimposed on each other, superposition is taking place, they are adding together. So, let's just recap. What I've actually done in this lesson is probably told you a little bit too much, if you like, but never mind. So let's recap on the things that you definitely need to know without me going in depth. Longitudinal wave, the particles move side to side and the wave moves to the side. Okay, if you've got that, good one. Transverse wave, the particles move up and down, but the wave travels to the side. If you can remember that, fantastic. All right, and you're going to have to be able to sketch the shape of one of these as well. I know I might have confused you by talking about longitudinal waves from sound being turned into transverse waves on a computer screen. Okay, and if you didn't pick that up, not a problem. But did you pick up the fact that if I've got two waves, whether they are sound or water or whatever, they can sometimes add together, which we call constructive interference, or they can sometimes cancel each other out, which we call destructive interference. So, as you might guess, this is sort of like the top end of the topic, the hardest part of the topic, and some of you may struggle to grasp some of these, and please give me an email if you are struggling with that, and I will answer and make another video if necessary, answering some of your questions if it hasn't come across. Now, there was one more objective, which was recall that all waves can be reflected. And we talked, when we looked at sonar, ultrasound, we used a sonar that reflected sound. Well, in fact, let's get the picture up. Reflected sound was an echo. My echo device is going off there. I shouldn't have said that, should I? Right.
Sorry, I don't know that one.
Right, thanks. So, yeah, all waves can be reflected. And if you remember from your light topic, that the angle of incidence, the angle it strikes the glass or strikes the wall or whatever, will be the same as the angle of reflection. I don't think the assessment in this topic goes in depth to labelling angles of incidence and angle of reflection, but you should have all done the light topic, so you should all be aware of that. But if you're not, reflection just means bouncing off something. And whether you're a longitudinal wave or a transverse wave, you can bounce off things, and that is reflection. And when it happens to sound, we call it an echo. All right, I said I wasn't going to spend much time on that because it's fairly straightforward. Let's take a look at just one or two of the questions here, just to see if we can pick up any misconceptions. Question 1, what is the difference between a longitudinal and a transverse wave? Hopefully you're all looking at that and thinking, longitudinal wave, the particles move side to side. Transverse wave, the particles move up and down. Hopefully you're thinking that. Question 2, which way will ducks on a pond move as the waves pass them? Hopefully you can recall that if I've got a duck on a pond and a water wave is passing this way, the duck will move up and down. It won't move sideways with the wave because the water is only moving up and down. The movement sideways is like an optical illusion, just like that Mexican wave. Yeah, people aren't running around the ground, they're just standing up and down. You drop a stone into a pond, what happens to some of the energy that was stored in the falling stone? Right, if I drop a pond into some water, that doesn't make any sense, does it? If I drop a stone into a pond, the energy that was in the stone, the energy that was stored in the stone, is transferred to the water. And that's what a wave is, okay? That's what a wave does. It transfers energy. So light is a wave, transferring light energy. Sound is a wave, transferring sound energy. When water moves, it's transferring kinetic energy. So there's kinetic energy in the stone, hits the water, and that kinetic energy is passed to the water, it spreads out. How could I make the waves on the pond with a larger amplitude? Well, I'd need to use a bigger stone, a heavier stone. I'd need to input more energy. Maybe even drop the stone from a little bit higher. Would possibly do as well. Let's have a look. I don't want to go through too many of the others because I've got a sneaky feeling they could be on your assessment. Yes, so I'm not going to go into too much more of those because I don't want to be giving the answers to your... I don't know what happened there. To your test away. Now, I do understand that that was a more difficult lesson than the others. Drop me an email if you've got any confusion about anything that I've just said. Anything to, anything to do with longitudinal wave, transverse waves. Just drop me an email and I'll get straight back to you. Okay. And how do I stop the recording? Bye-bye.